Francis Bach, that he's one of the experts in optimization in machine learning. So Francis did his PhD in Berkeley and now works in France with some kind of unique deal that he doesn't have to teach and is still being able to have an academic position in France. And yeah, what I would say is very remarkable of him is his kind of drive or fire to be able to, for example, like write a monograph of 90 pages by himself and just get it into trends or foundations in machine learning. And yeah, without further ado,
okay. So thanks a lot for the introduction and thanks for the invitation to come here. It's very nice. Very nice to be. Wait for the end, okay? Okay, so my goal today is to present like how and why convex optimization works for machine learning. This will not be like a list of tricks. I'm pretty sure that many of you have much more experience than I do in applying those algorithms to real data. Okay, the goal is to get the tools so that you can improve your own code. For example, for the newspaper you may be writing at the moment. So this being said, a bit of motivation. So I'm going to suggest that to give a set of examples which will be the motivation for this class. So okay, there will be a lot of data everywhere, so I don't need to convince you of this. And I will present examples where there will be two magic numbers. Throughout the talk, there will be the number of observations. This will always be n. And there will be the dimension of those observations or the number of features which are used for those observations. So let's look like where the money comes from. So advertising and search engines, whether you like it or not, whenever you type anything into like Google or Bing, there is learning going on. So what is NND in that context? So I'm caricaturing a bit what is NND, but N will be the total number of clients for a search engine. This can be billions. And D may be the total number of websites on the web. And for every person, those websites, those like search engines will record a 1 if you have visited a website and 0 otherwise. So for each person, you get a big, large, sparse vector. And from that big, large, sparse vector, you're going to predict which query you're going to output. So for me, when I say Tour de France, I love to do cycling. It outputs like the Rio Tour de France, the one for cycling. But beyond like making money, many problems in other disciplines are almost directly cast as a machine learning problem, and visual recognition is one of them. And so here, what is N and D? N would be the number of images you learn from, and you want to predict presence or absence of an object in the image. And D would be the number of pixels, or the number of features, or the number of hidden units in your neural networks, whatever you want. D will also be quite large. And a final example, oh no, so I cannot resist the temptation of showing my kids. So this is kid number 3, I guess. And so why I show this is because people talk a lot about big data, but some problems are very difficult, but are small data. Because they fit in my cell phone, and this is a very difficult problem because my kids look alike. And doing learning on small data is really something which is still important. And some problems are big, some problems are small. It's just to lower the hype on the big data aspect, on the big data. The key novelty is like everything is data driven. Sometimes it's big, sometimes it's small. With this being said, so last example, bioinformatics, just to give you a sense that there is life beyond Google and Facebook, and images and advertising. And one of them is saving lives, okay, bioinformatics. So here, you replace images by proteins, and you get essentially the same object, the same problem. So a protein is a complex object. It requires a lot of features to be described. It's a molecule in 3D. This is a complex object, and you have many of such objects. Essentially, many of the problems that people consider computer vision can be applied to bioinformatics by just changing the features, which I will go over. Okay, so this is the end of the pretty pictures. Now we can go into the more details, and the key will be to do large-scale learning where both D and N are large. Again, D is the size of each observation, and N the number of observations. And the key is to try to get this ideal running time complexity, which is I'm going to just look at my data, do a few operations, and then I'm done. Okay, so this is the goal of today. Of course, as soon as you set such a goal, you have to take into account prediction performance. Why? Because if I just predict 0 always, it is very efficient, or 0, but not very relevant. So from the start, as soon as you put running time into the picture, you have to mix statistics, how well I'm predicting on unseen data and optimization. And the key element in this talk will be to go back to simple techniques from the 50s. There has been progress, but it's not too caricaturing to say that this is essentially the Robinson-Monroe algorithm from the 50s. So this will be the outline of the class. So we'll first spend a little bit of time to review the concept that I need for the class, like complexity, smoothness, and so on. And then I will go briefly over the traditional way of doing of tackling those problems, which was to separate statistics from optimization. And then I will go over like classical context optimization, just a review of gradient descent and so on. This I will not cover. Okay, so yeah, I forgot to mention that those slides are available online. Okay, on my webpage. And if you want like the 18-hour version, which I gave at the master's class in Paris, you can also find it, and you can know more about like, the old school problems. Okay, so this is like review of stat, review of optimization, and then like mixing the two. So for non-smooth optimization, okay, well, support automation if you wish. Then for smooth optimization, where things can be a bit faster. And finally, we'll talk about like a recent line of work on using finite data sets to get like a better convergence rate. So throughout the class, don't hesitate to interrupt me if anything isn't clear. All right, so the setup. So I'm going to consider like essentially n observations xi, yi. So you can see xi as being an image, if you wish, and yi a real number coding the presence or absence of an object with this image. And I will always assume that data come ID. Okay, they come as independent and identically distributed. So I have a stream of data, and I get one pair whenever I want. Okay, so this is the key here. Throughout the class, I will focus only on linear predictions. Okay, so what is linear prediction? This is linear in the parameter setup. Okay, so I'm parameterizing my prediction as a linear function, and I put all the gory details into phi of x. Okay, so for every problem, in bioinformatics or vision, you can compute a phi of x. If you wish, phi of x can be like your neural network, okay, and just the last hidden layer of the neural network gives you a phi of x, and I'm mostly focusing on the theta over there, okay, the last layer. Okay, so I have a linear prediction in my parameter, potentially nonlinear in my x, and phi of x will be the vector of features, which I will always assume to be known and fixed. Okay, so I can compute a feature. Sometimes phi of x will be sparse. We have some zeros, sometimes not. Okay, so this is a generic formulation. So I'm going to consider like a regularized empirical risk minimization, which is very common. I will try to minimize with respect to my parameter. A convex data fitting term will be the average over my training data of the loss. So L will be a loss. I will show examples in the next slide. Between yi, which is my desired output, and my prediction. Okay, so this is a very common scenario, common in like many areas of applied mathematics. And I typically add a regularizer to avoid the buffeting. So what are the usual losses? So there are many potential losses, and in this course, I will focus mostly on the three types of losses. If you do regression, if your output is a real number, then square loss is by far the default loss, and we'll consider that as well. But one of the main focuses of the class will be on binary classification, where your prediction is labeled -1, 1, so just two possible values, and you predict as a sign of your linear function. The sign being 1 if you're positive, -1 if you're negative, and whatever you want if you're 0. So in that setup, the error that you make an error if y and your prediction have a different sign. Okay, so all the errors will be a function of the product between your label and your prediction, and you're going to make a mistake if that product is negative. Okay, so the error rate, the number of errors that you make, will be a function of that product, and this is open code of 0, 1 loss. This is the loss in blue. As you can see, this error rate is not a convex function of the product, y transpose like y times the linear function, So people have come up with convex surrogates. Okay, you replace your non-convex thing by a convex function. And there are three typical convex functions. The first one is a square loss. Okay, in turquoise. So essentially, you forget the fact that y takes value -1 or 1 to just predict, do these squares. So it's typically not very good because you over-penalize here. And then people have come up with other losses. So in the blue, in the red, this is the hinge loss. So this leads to the support vector machine, which is well known. And the key here that the red loss is non-differentiable at 1. Okay, so this talk will make distinction between smooth and non-smooth functions. Whenever I talk about non-smooth function, you should think SVM. Okay? And when I talk about smooth function, you should think about logistic, which is the loss in green over there. It behaves essentially the same way as a support vector machine in terms of prediction performance, but this one is a smooth function. Okay? So this is just a motivation for the class, but you can replace any loss. Okay, give me a loss, and then I can, if it is convex, I can use those algorithms. In particular, if you want to predict an output which is like a discrete object, which is more than 2 values, you have structured output SVMs, which are well known, and this may also fit that framework. So as a summary, okay, so this is the main motivating examples. Support vector machine, this is the hinge loss, it is non-smooth. Logistic, which is a smooth function, and least squares, which is also a smooth function. In a way, I'm going to define it soon, but it has a better, more properties. Okay, so I will essentially go back and forth between those three classes. So in terms of regularizers, so it's not a class about regularizers, so I will mostly not care so much about them. There are typically two main camps, a Euclidean camp and a non-Euclidean camp. So if you penalize by the square L2 norm, then you have access to kernel methods. I guess there was a class of kernel methods. And if you do want to put more final behavior into the problem, you can use L1 norm and a long sequence of extension of the L1 norm. And if you want to know more, I have a small book, a monograph with my colleagues on that. But essentially, this class is orthogonal to regularizers. Whatever regularizer you can plug in, okay? And in most cases, you don't even need a regularizer. Okay, and hopefully by the end of the class, this will become okay. So let's go back to my master problem. Convex data fitting term plus some regularizer, and I call theta hat any solution. So there are two quantities which are very important in that setup. The empirical risk, so f hat. So this is what you observe at training time. Give me your data, I can compute f hat, so f hat is this, and I'm minimizing it plus some regularizer. So this is what I want to minimize. This is what I'm actually minimizing. But what I really want to minimize is the expected risk, the error that I make on unseen data. Of course, I have to make a link between the data which I'm seeing and the data on which I'm going to predict, and this link is made by assuming that they come from the set distribution. Okay, so this is very standard setup. So we call that a testing cost. It is often called the generalization performance. This is actually a measure of your actual performance. It is useless to do well on training data if you don't do well on the testing data. So there are two main questions. The first one is to find theta hat. Okay, this is a pure optimization problem, and given the assumptions which I have made, this is a convex optimization problem. And the second one is statistics. Okay, how well does this perform on unseen data? So the key in this class is to do the two things at the same time. But before I do so, I will need to explain the two separately and then merge them again. Here, one annoying aspect, okay, this is, should you regularize or penalize? Okay, so this is the norm, the penalizer. I can choose to constrain, or I can choose to penalize. So essentially, these are equivalent. Okay, so essentially it means for any mu, there exists a d, and for any d, there exists a mu. But the problem is that there is no closed form formula between the two. So in practice, it's much more efficient to take that mu like this, because if you miss the optimal value of mu by a factor of 10, it will work the same. Here, if you miss the optimal value of d up to a factor of 10, it will not work. Okay, so typically, so why do I present the two? Because this is easier to analyze, okay, than this. Okay, there is a classical mismatch between theory and practice. So keep in mind that this is really what you want to do in practice. Okay, so this is a summary of the assumptions that I will need. Okay, I have data. Okay, I will assume that my features are bounded. So this will come up throughout the class. Those are my features. I control them. I assume they are bounded in L to the by R. Okay, this will typically be the only assumption that I'm going to make on the problem. I have bounded features. If you're not sure they are bounded, make them bounded. Okay, by clipping them. There's a piece of advice. Whenever you see a new data set, be sure that there are no outliers, and one simple way to remove them by clipping them. Unlike a risk on unseen data, a risk on my training data, testing risk, things which I will not observe. What will come up also a lot in this class is the risk associated with the loss, associated with a single observation. I will call that fi of theta. So give me a pair xi, yi, I can compute the loss. Okay, and by definition, as a consequence of being RID, for any I, f, my testing cost, is the expectation of fi. So this is just by design of the problem. So now I will look over like properties of my functions. I will always assume convexity, and I will need to make some regularity assumption. I need a way to differentiate between like non-smooth and smooth, hinge and logistic. So let's go over them briefly. So before that, convexity, because this is a convex function, I guess you know about that. So typically, this is defined as being something like that. It's always below its core, so very, very classical. We rarely use this in optimization. We typically use the other definition, which is that a convex function is always above its tangents. Okay, so I'm going essentially to use that twice, I think, or a few times in this talk. Okay, so this is the usual definition of a convex function. And the key with this is that this gives you a way to measure distance to optimum. So in our case, we want to minimize functions. Okay, so we want to get to that point. And how can you get like a notion of how far you are given the gradient? Okay, so the idea is that if I have a big gradient, I'm supposed to be far. And if you apply this with theta 2 being the optimum, okay, so I let you see that what you get is that g of theta minus g of theta star. So theta star in this talk will always be the global minimizer of the function. So this is a positive quantity, and this is less than the gradient at theta transpose theta minus theta star. Okay, this is just applying this with theta 2 being theta, okay, so theta 2 being theta, theta 1 being theta star, and you exactly recover, so this is essentially, so this is theta, this is theta star, and that quantity is simply that. Okay, so I will need this later on in the talk, so I'm keeping this. This is very, very simple convexity. Okay, and so typically when you see a problem, you want to check if it's convex or not, and the classical definition is having like non-zero eigenvalues of the Hessians. Okay, so G prime will be the Hessian of the function G, will be like a symmetric matrix, and being convex implies that this matrix is positive semi-definite, so only positive or non-negative eigenvalues. So first, maybe why convexity? So this is maybe like there are several reasons for convexity. The first one is the fact that it's very easy to check optimality. You just put a gradient equal to 0, and this is a global optimum. And the key difference with non-convex problem is that when you have a non-convex problem, many nasty things can occur even though the gradient is 0. It can be a local minimum, okay? But it can also be a stationary point. Okay, so it can be like a pass when you do like hiking. You see that at the pass, then you have 0 gradient, but it's not a local minimum. This will not worry us so much in this class, but when I will mention open problems, it's important to think about like what is the real problem with non-convex optimization. Is this local minima or stationary points? Okay, so we'll see that later. We'll see. I don't know anything about it, but I will mention it again later. So this is like for us the key with convexity is that you get the global optimum. But you also have convex duality. So I will not use it so much in this talk. I guess 0. But keep in mind that this is important. And if you want to know more, look at the book by Boyd and Van Emst. Okay, so we need like three types of assumptions. The first one will be Lipschitz continuity. Okay, so essentially bounded gradients. Okay, so in this class, I don't want to spend too much time having the tightest possible condition. So essentially, if you assume bounded gradients, this is fine for me to be Lipschitz continuous. Okay, so in the context of machine learning, when do you have bounded gradients? You have bounding gradients, for example, if your loss has a bounding gradient. Remember that our loss functions, okay, are of that form, and what you can easily show that if the loss is a bounding gradient, then your overall function has bounding gradient, given that your features are bounded. Okay, so here, take-home message: almost all of my losses will have bounding gradients. Okay, so this is a very standard assumption. And typically, this is the one which is made for non-smooth optimization. Okay, so take the hinge loss. Okay, it's not differentiable at 1, but you can define a sub-gradient which will be bounded at that set. Okay, so all of my losses will end up being Lipschitz continuous. So this means bounding gradient. We will also need bounded second derivatives. Okay, so a function will be smooth. Okay, what I will call a smooth function will be a function for which so this is a gradient mapping. If I take the difference between two gradient mapping, this is big if the distance between theta 1 and theta 2 is big. So this is the tightest condition, but typically what I will use in this talk is bounded second derivatives. Okay, this is by far the simplest. I assume I'll be twice differentiable, and this means that all of the eigenvalues of my Hessians are less than the constant L. So L will be the magic number I will keep on using throughout the talk. So on the left, a smooth function, on the right, a non-smooth function. Okay, this is somewhat obvious. And for machine learning, okay, for machine learning, where our cost functions are averages of a loss function taken on a linear projection, then you can easily derive the Hessian of this. And what you can show is that if the loss is smooth, then the function will be smooth, and the smoothness constant will be the largest eigenvalue of your covariance matrix. Okay, so I encourage you to derive this on your own. So essentially, whenever you see a machine learning problem and the loss is smooth, so this includes logistic and least squares, then you're minimizing a function which is of that form. It's convex, but of that form, it's nice and smooth. Okay, so this is what I consider a weak assumption. Okay, so whenever people make assumptions, you have to consider is it really big, is it really strong, or is it not too strong. So here, when I assume smoothness, the only real assumption is my loss is smooth. Okay, on the data, actually the data are bounded, and this is really something which I consider as being weak. It may be strong for other people, okay, but I consider it as being weak. Okay, so this applies. This is true as soon as my loss is smooth. These squares are logistic. This one starts to be much stronger. Okay, so this is the finest concept you're going to see in this class. This is strong convexity. So strong convexity means what? Means that you're not only above the tangent. So this is being above the tangent. So this is a tangent at theta 2. Okay, taken at theta 1. But you want to be really above, and you want some strong curvature in every direction. So here, this is an example of a function which is not strongly convex, because at that point, the derivative, this is a flat part, so the tangent is stuck to the part, and the chord, the function is not strictly above this tangent. This one is strongly convex because at every place, when you write down the tangent, you're always strictly above, and you can, the further you are, the stronger the difference. So the simplification is to consider twice differentiable functions. Essentially, being strongly convex means that all of the eigenvalues of the matrix, of the Hessian matrix, are strictly positive. So to be convex, you just need positivity. But you need a strict positivity, and typically mu is its lowest eigenvalue. Okay, so the image you should have, and this I will come back to that once later, maybe after lunch, is now you have a magic ratio between mu and L. So mu is the smallest eigenvalue of the Hessians, L is the largest eigenvalues of all the Hessians. So mu over L is a quantity which is less than 1. And when it is quite big, your function, like in 2D, looks like this. So it's like a contour plot. So if you're a hiker, this is you're at the top of the hole, and you go down the hole like that. Okay, so when URL, if URL is large, this is called like a well-conditioned problem. Okay, it will be easy to optimize. But when URL gets smaller, what you have is that in some directions you don't move a lot. Okay, so this is a typical example where URL is pretty small, and as you can guess, optimizing here will be a bit difficult. Why? Because the gradient here will tell you to go there, so we end up oscillating a bit. So typically, those problems where URL is small will be hard to optimize, and those ones will be easy to optimize. Okay, so this is the standard. This is a standard condition number. So condition number is L over mu. So if you talk to a numerical analyst, be careful that they typically use like L over mu, but in optimization, U over L is a bit more natural. So is this a big assumption? This one I consider as being a very strong assumption. Why? So if you take our traditional machine learning cost, okay, which is an average over my training data of a loss, then let's assume you have least squares for the moment. Okay? If L is least squares, then the Hessians are all equal to the covariance matrix. Okay? This is just a straightforward computation, which is classical for least squares. And as you can see, now your Hessian is a D by D matrix, which is a sum of n terms of rank 1. So this means that the rank of that matrix is at most n, because you sum n elements of rank 1. So this means that if n is less than d, okay, so if you have more features than you have observations, then this matrix is rank efficient. So therefore its lowest eigenvalue is 0. And even if it is not 0, I take any real data, okay, I'm willing to make a bet. Take your preferred data where d is bigger than 1000, okay, at least sufficiently many features, and compute this lowest eigenvalue. Typically, it's either 0 or 10 to the minus 12. Okay, so the real value of mu is very small. So when people say I have a strongly convex problem, typically this is rarely true directly. Okay, this is true, but with mu is being very very small. Okay, so this is actually you need data with a invertible covariance matrix. Okay, and even if it is invertible, when mu is extremely positive, this value may be tiny. So this, of course, people have noticed this, and typically a traditional way to make a problem strongly convex is to add a strongly convex term. So if you take any convex function and add mu over 2 times the square norm, then you become mu strongly convex. Okay, so this is a traditional way of regularizing in a numerical analysis, often called like Tikhonov regularization. But here we have a problem. What is the problem? The problem is that we change what we optimize. Okay, so as an optimizer, okay, I receive a problem. I say I don't like it. We need to change it. It's fine. It's going to be faster, but it's not going to optimize what I want. So in statistical terms, you do create a bias because you add a term. Okay, you have a price to pay when you add a term. And typically, whenever you see like a penalty added to a problem in machine learning, you should think of that mu as a function of n, number of observations. As n gets bigger, that mu will go to 0 as n. Okay, so mu has to be small, has to tend to 0 as I get more observations, otherwise this is not going to predict what you want. In particular, if you take mu being infinity, that's a very well-conditioned problem, the solution is 0, and it's not very, very interesting. So in this course, we will essentially don't do any of that regularization. So as a summary of this, like those assumptions, I'm spending the time to make this very clear because I'm going to use them over and over. So essentially, body gradients, think SVM. Okay, whenever I say SVM or whenever I say body gradients, you should think about the SVM or the logistic. Smoothness, you should think of like logistic and least squares. And strong convexity, you should think about I'm either in low dimensions or I'm adding a strongly convex regularizer. Okay, so this is a summary of the conditions. Alright, so let's now look at the traditional way of analyzing this technique from a statistical term. Okay, so here I will be quite brief. My goal is not to My goal is not to make you experts in statistical learning theory. Typically, the way it is analyzed, so you take a compact set. So for simplicity, we're going to assume the optimal of a constraint set, with omega being a norm. And when the goal of statistical learning theory is to take theta hat, which is my empirical risk minimizer. Okay, so this is theta hat. It's a random quantity. F is my testing error. Okay, so I want to see how my estimator behaves on unseen data. I'm going to subtract the best possible predictor for my class of functions. So remember that I assume I'm doing linear predictions. So since I'm doing linear predictions, there is no way I'm going to do better than the best linear predictor. Okay, so this is what I'm subtracting. So this is a positive quantity. Okay, so from the start, as soon as I make like linear assumption for the predictions, then this is the best. This is the best I can do. And you see the excess on top of the best I can do. Typically, on that setup, you add and subtract that term minimum over theta in my constraint set. Why do you do this? You do this to separate two things. The first one is called the approximation error. This is a non-random quantity. Okay, nothing is random there, and this is the effect of constraining my problem to be in a finite norm. Okay, so this is the price that I pay because I'm regularizing. Is approximation error deterministic. This will go down to 0 as D gets larger. And this is the price of having only a random sample. Okay, so f of theta hat is random because theta hat is random. Okay, so typically, in learning theory, you divide this in estimation error and approximation error. And we will focus more here in this estimation error problem. And traditionally, what you can show, this is in fact quite easy, is that all this will depend on how much f hat and f are different. So remember that f hat is my empirical risk, f is my expected risk, and you want to see the deviation between f hat and f. Okay, so f hat is an average, f is an expectation, and it is known that the deviation has to go down to 0 as 1 over root n. If I fix theta, f hat of theta is the average of my losses minus f, which is the expectation, goes down to 0 as 1 over root n. This is like law of large number, or this is like control limit theorem. But the problem is that this is true for a single theta. Okay, so since we're going to optimize about multiple theta, you need a uniform deviation bound. So what I mean to be uniform, I need to consider the supremum over all theta in my class. Okay, so this is the key of like if you look at 20 years of learning theory has been dedicated to looking at that sup over a large class of predictors. Okay, if you take a single theta, this is easy. This is just like central limit theorem. But you want to take this uniform over a large class. And what you can show, and I will not go into the details, is that this will also go down to 0 as 1 over root n. Okay, so going from a single theta to a uniform a big set of theta does not change the rate. And at the end, you get those deviations as 1 over root n, which is standard. Okay, if you take any average, then they vary as 1 over root n, and this is true uniform. Okay, so this is the key is that, so if f hat and f vary as 1 over root n. So this means that if I get the global optimum of f hat, I will get the global optimum of f up to 1 over root n. Okay, so this is a standard way of analyzing those problems. So just to make things like very clear, for our setup, okay, if you assume linear predictor, which I will always assume, you assume bounded features, you assume like the Lipschitz loss, like SVM or least squares or logistic here, you assume bounded predictors, and here the funny aspect is that for the result which I'm going to present to be true, you don't need convexity. Okay, so this is a kind of funny aspect. And what you can show is that, that the supremum over all possible predictors between f hat and f goes down to 0 as 1 over root. Okay, so constants are not so important. You can get like bound in high probability or in expectation. Doesn't make a difference. Okay, so the goal is to get this 1 over root n straight. And the tools to do this is Rademacher averages. And if you want to know more, can look at the slides from my master's class, or you can look at the nice reference by Bush. The key take-home message here is that if you rely on statistics to tell you how many points I need to predict correctly, the magic number, if you make the assumption, is 1 over root n. Okay, so this is to remember. This is 1 over root n because I'm sampling because of sampling. As I will show later, this is called a slow rate. Okay, so this will be a slow rate. Fast being 1 over n. Let me skip this. Okay, and so what I will not do here is also in the statistical setup. If you're willing to put more assumptions, is the problem. Okay, if I'm willing to assume that the functions are only convex, then you can replace this 1 over root n by 1 over nu. Okay, and so this is only more for the experts. So you get an improvement at the scaling in n. It's faster, but if nu goes down to 0 as n, it may be slower. Okay, so I don't want to go too much into the details for that, but remember that the best we can do is 1 over nu in a statistical term. Okay, so this is for the statistical analysis. How well my exact empirical X minimizer is behaving. Okay, so here I'm assuming that optimization is solved. I get theta hat, the optimal minimizer of my empirical risk, and it's going to perform as well as the best in my class with a rate 1 over root n or 1 over nu. So this is for the global minimizer of my empirical risk. Of course, I know I have to optimize. So what I will do now, I will go to the second part of the class, which is trying to look at the classical methods for optimization. Before I do so, I'll take a few questions if there are any at this point. No? Yep.
Here, just at the end, you said that you have a rule of 1 over mu n.
Yeah.
Mu has to go down.
Yeah.
With n. And it decreases because it's low with respect to n. So you get the best of both worlds.
So when they showed that, okay, the question is, okay, mu tends to 0, but how fast will it tend to 0? And at the end, are you doing better than 1 over root n? So this is what they showed in the paper. So Kudaran, Servo, and Chareshwar, they show that if you take mu being 1 over root n, you recover the same thing. Okay, and this is a case of making no assumptions. Okay, so at the end, there is no magic. If you make no assumptions and you add the regularizer to preserve, so when you add the regularizer, you move your function a bit. Okay, so what you get is you pay an error of mu because of that. You get 1 over nu, so you get mu plus 1 over nu. If you take the optimal nu, it's 1 over root n. Okay, so there is no magic. Whenever you add a regularizer, you're going to pay it at one point, okay? And you pay it because you add a bias, okay? So you improve that term, but you add that term, and when you take the optimal trade-off, you don't get anything. Okay, let's look over like the classical methods for optimization. Okay, so here, in the next few slides, I will forget machine learning. I know it's possible to forget machine learning, and this will be done like for a few slides. I will take any convex function G. Okay, this is important because all of those techniques are blind to the machine learning structure. Our G's are very special, our functions are special, but here I'm going to forget about it. So I'm going to consider a gradient descent, okay, acceleration, Newton, and subgradient. I won't do ellipsoid. And of course, the key, why did I present all the properties of my function G? Because they're going to behave differently when you optimize. And remember that, and this will be like, this is the topic of the class, in fact, is that in machine learning, we don't have any function G. Okay, so this will be taken later. And if you want to know more about optimization, there is a nice book by Nesterov and a nice monograph by Sébastien Bibek. So if you want to know more, this is a good reference. So first, let's take smooth functions. This is the standard application of gradient descent. So I'm going to assume G is convex. It is L smooth, so I'm assuming like all the derivatives, all the second order derivatives are bounded. So H, this is like logistic or least squares. And I'm considering the gradient descent recursion. I go from step t-1 to t by just going down the direction of the negative gradient. So here in this class, I've chosen to get explicit step sizes, because the step size is that number, and here I'm taking it as 1 over L constant. So in practice, typically people do a line search. You try several values as long as the function is decaying. So this is very important in practice. Okay, in practice, if you don't do line search, it's going to be very slow. But the topic of today is more to understand why and how methods work. So we mostly focus on the constant step size, keeping in mind that in practice you have to be careful with that. Okay, so this is a random descent, and the behavior will essentially depend whether you're on that type of situation, like strongly convex, a well-conditioned problem, or that type of situation. Here you're going to be fast, here you're going to be slow. It's somewhat obvious. And this can be translated into precise convergence bounds. And what you can show is that if you assume strong convexity, okay, then the convergence is said to be linear. So this is a very bad name, linear convergence. I call it geometric or exponential. Okay, so but the traditional way in the numerical analysis is to say linear convergence. Why? Because the number of significant digits grows up as a linear function. At the end, it's geometric. What does this mean? It means that if you start from theta 0, can be anywhere, typically 0 for machine learning, then this is a distance to optimum. So whenever you look at bounds, you have to be careful what is tending to 0. Okay, so here I'm considering the difference between theta star, this is the my optimal point. So g of theta star, this is the excess of g. Okay, this is always a positive value because theta star minimizes g. Okay, so this tells you that theta t has the same value as theta star. Okay, or the excess of the value of theta t on top of the one of theta star goes down to 0. What I will sometimes use is the distance to optimum. What is the distance to optimum? This is theta t minus theta star. Okay, so this may look like a subtle difference. Okay, so this is just I'm going to predict as well as my optimal predictor. I'm going to tend to my optimal predictor. So typically in machine learning we prefer those because those are sufficient. We just care about the best possible prediction, and being close to the optimal predictor we don't really care. And worse, in many cases, there is no such unique optimal predictor. There may be several of those, so there will never be convergence with that value, but you will always have convergence with that value. This being said, for strongly convex problems, you can also get convergence with indirect values. The key is that at every time step, you cut down the error by a fixed amount. Okay, so if you do t iterations, you multiply this t times, and as I will show, it is a 3-line proof, and which is 2 lines when we do this squares. I will do it. And the key is, again, so you can do line search, okay, or you can do like exact line search or not exact line search. For gradient descent, everything is simple. Of course, the problem is that convergence rate will depend on this strong convexity constant. So when mu gets to 0, when I get to high dimensions, then I multiply the factor which is very close to 1. So I'm not reducing a lot. And if mu is 0, then what I get is that from that bound is that the distance to optimum in function values does not increase. Okay. But what you can show is that if you just assume convexity, is that the same quantity, okay, goes down to 0 as 1 over t. Okay, so 1 over t is much slower than exponential in t, and this depends on how far you started from any global optimum. So why this 1 over t? Because of this effect. Okay, you have oscillations. Okay, so you oscillate, and at the end you end up always converging, and much slower than making a big step like that. Okay, so this is the way gradient descent is behaving, and this is just like putting words or putting like equations or bounds into a well-known problem. Is that some problems are difficult and some problems are easy, and in a sense, it is not the fault of gradient descent to be slow. This is the reason is the problem may be hard. And the key on the positive side, gradient descent is adaptive to the problem. In the sense that you never need to tell gradient descent if you're going to have a simple or a hard problem. Just run it, and it does the best that it can. This is on the positive side. On the negative side, you can do better. Okay, and I will show acceleration in a few slides. Before I do so, I want to spend like 2 minutes showing those convergence rates for least squares. I do believe that least squares is a good exercise to understand where those equations are coming from. So let's look at the squares. So this is a quadratic convex function. Okay, so this is a quadratic term, this is a linear term. So it's well known that the global optimum is attained by h minus 1 times c, because the gradient is h theta minus c. Okay, so this is the global optimum. Then if I use my gradient descent recursion, so this is the recursion, this is the gradient of that function at theta, okay, this is a affine function. And I can use the fact that c is h times theta star, okay, I can replace this by that. And now, if I subtract the any optimizer, I get theta t minus theta star is equal to theta t minus 1 minus theta star minus this. So at the end, I get this very simple linear equation. Okay, so this is always the case. Whenever you use these squares and you do like gradient descent, this ends up being implicitly multiplying matrices over and over. So since this is a linear, one iteration is multiplication by a matrix, t iterations is multiplication by the power t of that matrix. Okay, this is very standard. And now what I have to do is to analyze what's happening when I take the power of a matrix. So this is very, very classical. And that matrix is a very nice, well behaved. Why? Because H is the Hessian matrix. Okay, so H is positive semi-definite. H is symmetric. The largest value of H is L. So this matrix, identity minus 1 over L times H, has all of its eigenvalues between 0 and 1 minus mu over L. Okay, so the lowest eigenvalue of H is mu. So the lowest eigenvalue of H over L is mu over L. So the largest of that is 1 minus mu over L. So now I'm taking powers of a matrix which is positive. So all of the eigenvalues will be powers of the eigenvalues of the original matrix. So all of the eigenvalues are in that segment. Okay, so very standard application of linear algebra. And now if I take the norm of that, okay, the norm of that is the norm of this times, or is less than the norm of that times the largest eigenvalue of this. Okay, and now since the largest eigenvalue of that matrix is 1 minus mu over L, I get this 1 minus mu over L power 2t at the right. Okay, so this is like a one-line proof of where the mu over L comes from. It comes from the contraction of that linear operator. Okay, so this is like the one-line proof that will get you to this linear continuous rate. The problem is now, what happens when mu is 0? Okay, so let's take the exact same reasoning when mu is 0. I'm convex, but I am not strongly convex. Then all the eigenvalues of this are between 0 and 1. So I get like, I don't get like a straight contraction, so I can't apply this anymore. And this is where you see the subtlety of going from convergence of iterates to convergence of function values. So now let's look at this like convex case. There is no convergence of iterates. Okay, so you don't augment the distance to any optimum. So the way to do it is to consider that you do the distance to optimum using function values. And the key is that the distance to optimum using function values, okay, I should write it here. The distance to optimum for function values is so g of theta minus g of theta star is simply 1/2 of, it is the same error, but I multiply by h. Yeah. Okay, so the only difference between the distance to optimum here and this one is the presence of h. Okay, what does this mean? This means that whenever I'm calculating the distance to optimum, okay, if h is not varying too much, if the value is small, then I don't care so much. Okay? So this means that when I take distance to optimum, I have to multiply that matrix by h. So this means that when the eigenvalue is 0, it's a case where I don't vary anywhere, I don't vary along that direction. So I don't care about it so much. So in mathematical terms, this means that the distance to optimum will be bounded by the maximum eigenvalue of h times this, and this is the maximal value over that interval, because h has eigenvalues between 0 and L of v times that thing. Okay, and you can easily see that that thing, okay, the maximum is L over t. So y is just using v minus v over L to t is less than v times the exponential of minus 2t v over L. Okay, it's just 1 minus x is less than the exponential of minus x, and again v exponential minus v, and this is not to be small. Okay, so I will not do all the details, but the key is to understand that the difference between converging of the iterates and converging of the function values is the fact that we don't care about like directions where the function is not moving. Okay, so this allows us to get this convergence as 1 over t in a very simple way. Okay, so this is for quadratic, and for non-quadratic, the principle is the same, but it's a bit more complicated. Any questions on value descent? No? Let's go over now for acceleration. Okay, so what is acceleration? It's a very simple technique from Nesterov in the 80s, and the way it works is you're going to do gradient descent, okay, but you apply it not to your current iterate, but to a so-called interpolated iterate. Okay, so you take your current iterate and you move it a bit in the direction which you took from θt minus 1 to θt. So it's often called a momentum technique. So it's not exactly equivalent, but essentially equivalent to momentum. And what we showed is that by using this like two-line modification, you go from 1 over t to 1 over t squared in terms of convergence rate. And this is a big deal, okay? Because when t is 1,000, okay, t squared is 1 million, so it's 1,000 times faster. And of course, whenever I show a bound, it is an upper bound, okay? So big caveat, there is an equality here, okay? So it's not because I have a bound that the methods do work better in practice, okay? Sometimes there is a mismatch between theory and practice, but for that one, there is indeed an acceleration for that. The proof is a bit more complicated, and when I say 10 lines, it's like a bit more than 10, and I think we have a short proof with my colleagues if you want to know more. The key now is that this is not improvable, in the sense that it's not possible to do to improve that at all, and it does extend to strongly convex functions. So this is exactly the same algorithm, but that term is now different, and I won't go so much into the details. But whenever you see gradient descent, you can always accelerate it. Yep.
So can you go back to the previous slide? What do you mean by not improvable? Is it the bound?
The bound. This means that yes. What is not improvable is that if you find an algorithm so that after t iteration, t being less than dimension, you improve on that bound, then Nesterov is wrong. So I would say you're wrong. Okay? But, okay, so I will show examples like this afternoon about like a more precise like lower bound. But in that kind of optimization, you have like people that do algorithms. Okay, I call them the optimistic guys, and people doing lower bounds. I call them the pessimistic guys. Okay, some go to nip, some go to cold. Okay, I let you decide. And don't repeat this, by the way. And so typically, they're happy when the upper bound matches the lower bound. Okay, when there's an algorithm achieving the best possible you can do on that class of problems. The problem with lower bound is that it's the best possible you can do on the given class of problem. And you have to be careful about the class. And here the class is the set of all smooth functions in dimension. Yep.
We have bound for convergence in function. Do we have any results for convergence in argument?
It won't converge for iterates. Okay, same thing as here. Okay, so if you don't assume strong convexity, there is no reason to have a convergence. Why? Because there may be multiple theta star. Okay, so what you can show often is that the iterates converge to any of the global optimizers. Okay, this often you have, but this requires much more intense math. Okay, So typically, if you're strongly convex, convergence of iterates of function values is equivalent. If you're non-strongly convex, you always have convergence of function values, okay, like this, but you may not have convergence of iterates. Okay, so now before I move on, what happens if you have like an L1 norm? Okay, if you want to put a regularizer on top of the problem. Okay, so this is a situation common, like in learning and signal processing. And before we can see how we're going to do it, we have to reformulate gradient descent. So one way of formulating gradient descent is so-called the proximal method. Okay, so the way proximal methods are defined is at every time step, I'm going to do a Taylor expansion of my function around my current estimate. This is my current value. Okay, this is my linear term. So this is my first order Taylor expansion. And since I want this to be valid, I'm adding a penalty term to stay close to my iterates. Okay, so I add a penalty term like that. Okay, I want to stay close to my iterates. Now what I have, as a function of theta, I get a constant term, linear term, and quadratic term with like no Hessian. So if I optimize over theta, okay, if I compute the gradient, here I get gradient, I get L times theta minus theta t. When I solve, I get this. So in a sense, gradient descent is a proximal technique, okay, which is obtained by replacing a function by its first order Taylor expansion plus some penalty term to stay close. Okay, so this is kind of useless. You don't need to know this to write gradient descent. But now, if you add like a non-convex term which may not be smooth, okay, so you assume you're in a setup where f is smooth, like a square loss or logistic loss, but you add, let's say, the L1 norm. So the L1 norm is not smooth, okay, you have a kink at 0, and you can't apply, it's not easy to apply gradient descent to the L1 norm because it is non-differentiable. Okay, we'll show that in the next few slides, but you're going to get a slow rate. To do this, you can use the exact same technique, namely that we're going to take that function and take a Taylor expansion of the smooth term f. Okay, this is still a constant term times the linear term. I still add the proximal term to make sure I stay close to my iterate, and I don't change the non-smooth term. This one I keep intact. Okay, so this is typically like my non-smooth function. The key here, okay, is that now the problem may be easy in theta. Okay, why is it easier than this one? Because now in theta I have my norm, my penalty, I have a linear term, and I have a quadratic term with no Hessian which is diagonal. So this term, this is typically much easier to solve. And what you can show, and this is on the slide that I don't want to do it, is that if you take the L1 norm, okay, solving this is equivalent to taking the gradient and setting the small components to 0, okay, and shrinking the other ones to something which is a bit smaller. It's often called like iterative soft threshold. So whenever you have like a norm, okay, you can use those techniques, and this was like first done by Nesterov and Beckentable, and we talk about this in our monograph. And the key here is that here we get the price of non-smoothness. We can do a non-smooth function like it was a smooth function. Okay, so this is a non-smooth term, and if we know how to solve that step efficiently, then we can get the rates from smooth optimization. Okay, so whenever you have a sparsity-inducing norm, often you can compute that term easily. This is a case for. Okay, so now let's move on from gradient techniques. What about Newton? Okay, so if you have taken a class optimization, Newton is often given as being as a really good optimization technique, and it is really good, okay, in a sense very bad. So let's look at why is it so good and so bad. So the principle is the same as the gradient. So you take a Taylor expansion around your current iterate, constant term, linear term, but now you keep the quadratic term, and if you want to solve that one, you set the gradient to 0, and you recover this iteration where you replace this constant by a matrix. So why is it bad? Because you need to solve a linear system, which is decubed in general. So when v is 1 million, this is going to be hard. But the good aspect is that this does converge in a very small number of iterations. What you can show is that it has quadratic convergence, is that once you get close to the optimum, that the distance to optimum is squared at every iteration. Okay, so this makes it converge very fast, and there is a nice chapter on it in the book by Freud and Daniel. So if you care about having a very high precision, and sometimes you do, okay, then Newton is for you. But if you don't care about getting a high precision, Newton is not for you. Yep.
Has there been some composed methods that you start with the gradients and at the end you do one or two steps of Newton to really prove at the end the precision?
This is called the one-step estimation statistics, and I will present it later on. Okay, as a summary for like smooth optimization, we have still essentially two techniques: gradient descent and Newton. And the key is that what decides if you're easy or hard will be the strong convexity of the function. If it's strongly convex, well conditioned, it goes down linearly as a geometric sequence, and only 1/t otherwise. And you see the effect of ill conditioning. You get it gets much slower. This is not optimal. You can improve that using external acceleration, and those are the optimal rates. And Newton is quadratically convergent. Now what we do now and until the break is to look at non-smooth optimization. Okay, so those only apply to smooth optimization. What can you say about smoothness? And we need to assume to look at the subgradient technique. Any questions on smooth optimization? Yeah?
You said before in the complex case that the gradient descent did not compare to the iterates.
Yeah.
If you have diminishing step size, that's converge.
So if you so here in gradient descent, okay, let's take the simplest one. So here gradient descent, if you're not smooth. What is the question about that?
Yeah,
for smooth functions, having decaying step size does not help. I'm not sure. I think it's issue of iterates converging or not. Some people care about it. I personally don't. So I don't know all the details, but maybe I don't know. Question on smooth optimization. So before I go to non-smooth optimization, a word of caution. Okay, some people, and I was one of them long ago, was saying non-smooth is it just for mathematicians, just apply gradient, find a gradient, just apply it, and you're fine. Okay, in fact, I had a similar than this week NIPS deadline. 10 years ago, and we had a non-smooth optimization problem, and we were doing gradient descent. It was working perfectly well, and then we tried another data set, not converging. Okay, and we tried, put some noise, we tried, it was late at night, and then we said maybe it's because of non-smoothness. Okay, and what was happening is something of that form, is that simple techniques on non-smooth optimization may not converge. And sometimes will not converge even in practice. It's not how can I say this nicely? It's not like mathematicians being too picky. It really happens. Okay, so if you forget about non-smoothness, it can hit you. Okay, so this is the classical counterexample from Bertsekas. Now this is the contour plots of non-smooth function because you have kinks here, and if you start steepest descent from any place here, okay. Then you're going to see a smooth part, you're going to converge to that point. Okay? You never reach it, you always get very close. So you will converge to here, but here you have a direction of descent which is over there. Okay? So it's a case where steepest descent will not converge. There are multiple examples for also coordinate descents that will not converge if you go non-smooth. So a word of caution, don't treat non-smoothness too lightly. Alright. So now let's look at what works, and this goes back a bit to your comment about like decaying step size. Then if you start to replace this constant step size with a decaying step size, then it will start to work. Okay, so this is the setup that we're going to consider. A convex function, okay? We need to assume Lipschitz continuity of just a non-smooth function, okay? So it can be also, this applies to the SVM. I'm going to assume a compact set, and I'm going to do like a projected subgradient. So why projected? Because I'm going to assume I'm optimizing over a compact set for simplicity and for the bounds that I will show later. So I start from my iterate, I do a gradient step, okay? Now I'm assuming a decaying step size as 1 over root t. Don't care so much about the constants, it's 1 over root t which is important about there. And since I don't belong to my constraint set, I'm going to put back a projection, okay, which is orthogonal. So if I optimize over the set of constraints, I make a step like that, I may get out of my constraint set, I project again, and then move on. Okay, so this is the so-called projected subgradient technique, which is very simple. So what we will show, it will be the second proof of the morning, and then I think I'll stop, is that the distance to optimum in function values goes down to 0 as 1 over root t. Okay, so here you should see the difference between like smooth and non-smooth. We went from 1 over t to 1 over root t. Okay, this is slow. Okay, so 1 over root t is going very slow. Okay, so this is essentially, and this is the best we can do. Okay, with a similar reasoning. If you give me a problem on which you can improve over 1 over root t, then you're wrong, because Nesterov has shown this is not possible. Okay, so let's begin. So let's look at the proof, because the proof is a bit longer than for gradient descent, but the key is that it's quite basic and also gives you hints why going stochastic will be very easy. So let's go over it. So this is my iteration. Okay, projecting gradient descent. I have a step size, which I keep like this. So my assumptions: I am assuming that the gradient is bounded. I am assuming that my iterates are bounded. Okay, because I'm doing projection. And whenever you try to prove something about optimization, you need a concept of a Lyapunov function. What is a Lyapunov function? It is a function that will go down along my iterations. Okay, and hopefully that function going down will tell me that I'm converging. So typically, you have two natural Lyapunov functions: distance to optimum, one of them, or distance to optimum in function values, like this one. Okay, so there are not like so many choices, and so here we consider the distance to optimum, and the goal is to go down. Okay. So first, we're going to see that. So what is theta t? This is the projection of this. Theta star is the optimal value. So this is the projection of itself. And what you know is that if you do projection, you can only reduce the distance. Okay, so this is often called a coercitivity of projections. And so from the start, you can start by forgetting about the projection and just taking theta t as being theta t minus 1 minus this. Now I can expand the square. Okay, so it's really important to have the square norm, the Euclidean norm, to get the product. You expand the square, it's that term square. You take the square of that term, which is this one. But here you get the gradient of g prime, which I have assumed to be bounded. So I get this square like this. And now I get the cross product. Okay, so this is just expanding. Now I can use the fact that this quantity, okay, remember, is a surrogate to the distance to optimum. And it's still over there. Okay, so this is the consequence of convexity. And this is the only place I'm going to use convexity. Is not almost the only place I'm going to use convexity. So this quantity is a surrogate to optimum. So now this quantity will be dominated by that. And now it's over. Okay, now the proof is over. Now it's just like manipulations to get what you want. So now if you isolate this distance to optimum alone, okay, you put it there. Okay, this means that you have to divide by 2 gamma t everything. Okay, so this is that term divided by 2 gamma t, that term divided by 2 gamma t, and this one divided by 2 gamma t. Okay, so I'm just shuffling around and isolating that term So the distance to optimum measured in function values, okay, will be something like that. So here you see appearing something very nice. You see the start of a telescoping sum. Okay, if I'm going to take the sum of that, it's going to make the sum of that, and we have terms that we telescope. So for this, you need gamma t to be constant. Okay, so for simplification, I will first assume that gamma t is constant. This is often called the known horizon setup. Okay, so I know I'm going to optimize for t iterations. Okay, and I'm going to have a step size which is constant along those t iterations. So of course, that step size is allowed to depend on the horizon t. This is what I'm going to do. And if I do this, gamma t equal to gamma, then if I take the sum of that from 1 to t, then I get the sum of that from 1 to t. But since gamma is constant, I get this, and I get that. But now, since gamma is constant, okay, I get a nice formula there. This sum will telescope, okay, and I just get the first one. So at the end, what I get is the sum of all my distance to optimum will go down to 0. And you always have on those bounds something that will tell you that it goes up when the step is too big, and something that goes down when the step is too small. You have a trade-off for the step. So the step size is gamma. So if gamma is too big, then the error in my gradient will hit me, and if gamma is too small, I'm not going to converge. And the base multiple gamma, you get gamma here, 1 over gamma, here's that one, and those depend on the horizon, and what you obtain that the average of that will go down to 0 as this. And now what you have is the average of the function values, and this dominates the function value at the average because of convexity. Okay, so Jensen's inequality. So overall, when you assume a constant step size, after like a small proof, you obtain that the value at the average iterate minus the optimal value goes down to 0 as 1 over t. Okay, so this I've just used very simple like way to obtain this, and then it's just algebra to get this. So here, of course, this is not satisfactory because in optimization it's always nice to have this anytime algorithm. I launch it, and when I'm fed up, I stop. Okay, so standard way of doing optimization. So you will need to replace here gamma t by this that depends on t. So this you can do. It takes a bit more while, and you get the exact same bound. I won't go over it. Okay, so this is the exact same thing. Okay, this is what you have here. Okay. So now let's try to combine it with statistics. Okay, so the goal was to do machine learning. So let's do combine it. And this is one of the master slides of this class. So remember that what we saw earlier on was if you make some assumptions like linear predictions. So now I'm focusing on a specific set of problems, and I take f hat being this like empirical risk minimizer. I'm assuming some stuff. Forget about that. We saw that uniformly over all my predictors, the empirical risk f hat and the expected risk f was the difference was only 1 over 10. So this means that whenever I optimize f hat, okay, I get the optimum of f up to 1 over 10. This is the statistical part. From optimization, what we just obtained, if you apply stochastic subgradient descent to that function, is that f hat, the distance, the empirical risk at my estimator, obtained by doing t steps of subgradient, minus the best possible empirical risk for all of my predictors, goes down as 1 over t. This is an optimization result. This is a statistical result. Okay, so here there is nothing random about that. Just give me f hat. I know that if I do t steps of subgradient, I get 1 over t. Okay, this is pure stat. Give me n observations, then the f hat and f will vary. The difference will be going down as 1 over 10. So what this suggests is, if you want, there is no need to optimize f hat up to the end. If you just take t equals n, okay, the error that you make because you optimize only partially is 1 over n. So this combines nicely with the other one. So if you do t equals n steps, then what you get is you may replace those bounds by theta hat being this approximate minimizer. Okay, so essentially you want the often called the optimization error to match the statistical error. This is achieved when t equals n. Okay, this is fine. What is the problem? The problem is that when n iterations of subgradient descent, I have to compute at every time step the gradient of this. Okay? And to compute the gradient of that, it is a sum, so I have to go through my entire data set. Okay? So every iteration of subgradient on that full thing is O over n. If I make O over n iterations, overall, I get O over n squared complexity. So here, what do I have d? Because every time I compute the subgradient, I have to add vectors of size d. So every subgradient step is O over nd. Okay, so if you make n of them, you get O over n squared. Okay, so this is the standard result when combining statistics and optimization done separately. Okay, so here, this has nothing to do with optimization. This has nothing to do with statistics. You combine the two, and you get a complexity of 1 over of O over n squared d to achieve this 1 over 1. Okay, so this is the goal of the class, to remove the square. Okay, but keep in mind that standard practice, if you just take your data and minimize the empirical risk, you're going to end up with something similar. So here, I have chosen that non-smooth optimization to do this because it's very nice and compact, and the two terms exactly match. So this is true in all cases. Whenever you minimize the empirical risk, you need to lose a bit compared to what I'm going to show now. Any question on that important slide? This is really the key thing to understand. Okay, so, and what I have left, I think I'm done.
Sorry. The first statistic part depends on the delta we aim at. So the choice equal n should depend on delta too. No?
Small delta? A good point. So here, my goal was to avoid those considerations of high probability. Okay, so typically, you could replace it by an expectation, and then the data will go away. The same to right, but typically, yeah, let's not get into those. We can talk more offline if you prefer. Yep. So what I've left before the break, I'm getting hungry, is like strong complexity. Okay, so here I will not give the details, but I will just, if you assume strong complexity and non-smoothness, you can improve this 1 over ρt to 1 over μt. Okay, and this is done by the exact same algorithm. Okay, but you take a step size of that, you take a big different averaging, and at the end you get this 1 over μt, which is also the best you can do. Okay, so this is quite simple. If you want to assume strong complexity, you get 1 over μt, but keep in mind that mu may be quite small in practice. And the proof is the same. Okay, so now just as a summary before going to lunch. Okay, so I presented like quite a bit classical techniques to do like complex optimization, and those techniques were applied to the machine learning structure of the problem. So we have seen like gradient descent, essentially the classical technique. So this is gradient descent, this is for smooth functions. If you have like a non-smooth function, you may need to do like some gradient, which is essentially the same, maybe a projection. And what we saw is that it's 1 over ρt if you assume nothing, non-smoothness. So just like 1 over t if you start to assume smoothness, exponential if you're strongly convex. Okay, this is what we saw. We saw Newton, which is much faster but not really useful in our setup. And the key for the rest of the class is to achieve those two things. So those are key insights by Léon Bottou and Olivier Bousquet. The first one is we don't need something like this. We don't need to optimize up to machine precision. Why? Because our cost functions are averages. So in a sense, they vary naturally with a deviation of 1 over root n. And before 1 over root n gets to 10 to the minus 16, we need like bigger data. Okay, this may come up at one point, but I don't think we need that for the moment. Okay, so this is not useful. First key insight. Second key insight is our cost functions are averages. Okay, we don't have any G. Our G is an average of terms. So maybe you can leverage this to do optimization. And this is why after lunch, I will mention the stochastic approximation. And this will be the topic of the main topic of the second lecture. So what is the summary? Okay, so the summary will be a summary of rates. And essentially, I will populate that table with the stochastic terms. Okay, so it's important to realize all those terms. I have like hardness of the problem in terms of loss functions. Okay, like SVM, logistic, least squares, just convex, strongly convex. Okay, so you're supposed to be faster in that direction and faster in that direction. Okay, so what we've seen is that it's the most basic case, the slowest you can be if you make no assumption is like 1 over root t. Okay, so this is for non-smooth, just convex. It improves to 1 over mu t if you're strongly convex. On the smooth case, we saw 1 over t squared for acceleration. Improves to exponential if you're strongly convex. And quadratic did not help. Okay, quadratic functions did not really help, and we had the exact same bound for quadratics. Okay, so the main goal of the class this afternoon is to populate this with stochastic techniques. Okay, so what we will see is that line will not change at all. Okay, so for stochastic technique, in fact, using the stochastic gradient will not change anything in terms of rates, but it will change in terms of computation. Because now you replace like a full subgradient, which is O over n, by a single gradient, which is O of 1. Okay, so this is where the game will come from, and then we'll go over that, which is where things will be a bit different. Okay, so I've covered that part, and so what I will do after the break is go over non-smooth stochastic optimization, and as you will see, this will be the exact same proof as for subgradient. I will just need to add a few expectations, and then I'll go over smooth functions. And why do we need smooth functions? So one food for thought before getting real food is take that bound. Okay, that bound is nice, it's sharp, it's very optimal, but there's a problem. The problem is what? If theta 0 does not appear in that bound. Okay, so that bound does not tell you that if you start at the optimum, you should do better. Okay. And this is a problem. Okay, so typically, if you start close, you should do better. Okay, and this is for non-smooth. For smooth function, we had something like that. For smooth functions, we had something like that. If you start close, then it's helpful. Okay, so essentially, when you go from non-smooth to smooth, you can start to have a nice trade-off between hardness of the problem and how far you start from the optimum. Okay, so this is key in practice. If you start closer, you should behave better. So this we will do by going smooth. Okay, and then we'll go over the least squares, where we can do even better. And finally, like quickly over final data sets, where we're going to improve this 1 over t to an exponential. So thank you for your attention, and I can take questions before lunch.
Sorry, what do you mean by finite data set? Because the whole world is finite. So.
This is the whole world is finite. That's true. I agree with that statement. But what I will mean is that for machine learning, I will mean that I will be able to make several passes on my data. Okay, all the band I will show for stochastic gradient will be you make a single pass over your data, then you stop. And then all our bound will be not on the training error, but on the test error. Okay, so they will tell you what you predict later on. The problem is that often you make several passes, and this is what I call like a finite data set.
Just, it's not a really question, it's more, I'm wondering, like, you look at the proximal predict, networks that sort of combine non-smooth with the smooth, they get rates that are around 1 over t
Okay, so the question is, what if I have the L1 norm plus a smooth term, and so smooth, so here I should add smooth plus all proximal methods. Whenever you treat the non-smoothness by splitting or by using a proximal operator, it goes into the smooth category.
So then what? In which situations you cannot do that?
You can always, whenever you can only do it if this operation is simple.
Okay.
So if your non-smoothness is so complicated that you can't do this, then solving this is as hard as the original problem. Okay, so this is okay. All right. So I guess see you at webinar 2.
Sí, por favor, hazte que hacia el mercado, hay una
Vale.
está al lado. Que yo fui a comprar uno de los. Hay un sitio que es bastante malo, pero el otro no está mal. Podemos ir a ese otro.
Ok.
Que sí, porque no sé.